Alright friends, welcome back. In this video we're going to go ahead and move on in our discussion of graphing rational functions, and we are going to go ahead and talk about oblique or slant asymptotes. So you may remember from the last video lesson that if we take a look at a rational function, which remember is just a polynomial over a polynomial, the degree of the polynomial in the numerator on top, that's going to be something that we denote as capital N, and then the degree of the denominator is going to be capital D. And what we said in the last video is in the case of horizontal asymptotes, that if the degree of the numerator is larger than the degree of the denominator, then that automatically means that you don't have any horizontal asymptotes to worry about. But we did point out that if the degree of the numerator is just one more than the degree of the denominator, then there is going to be an oblique asymptote, okay, or a slant asymptote, or in other words, an asymptote that is more diagonal as opposed to horizontal or vertical. So what that's going to mean for our purposes is if a graph has an oblique asymptote, okay, so if this is something that you already know, if it has an oblique asymptote, then that automatically means that it's not going to have a horizontal asymptote. Okay, so that is something that you don't even need to worry about if you notice that it already has an oblique asymptote. And so I've left some steps here for us to be able to go ahead and graph rational functions with an oblique asymptote. The very first thing that we need to do is always look out for those vertical asymptotes. So again, setting the denominator equal to 0 and then solving for x. That is going to give you a vertical line or a vux that looks like x is equal to some number. And then what we're going to do is we're going to look at those degrees, right? Again, if the degree of the numerator is just one more than the degree of the denominator, then you're going to have an oblique asymptote. And in order to find it, we're just going to use some long division. So we're going to divide the two polynomials by using long division, and the quotient that we get from that is going to be the oblique asymptote. And you'll see here that I wrote it as a little bit of a note. The oblique asymptote is just going to be the quotient without including the whole plus remainder over divisor part at the end. Okay, and then after that, we're just going to go ahead and pick 2 points to plot and then sketch the rest of the graph by hand here. So I'll go ahead and take you through this first example. We just need to go ahead and graph this rational function and then identify all the characteristics below. We have f of x is equal to x squared minus x, all divided by x plus 1, and we just need to go ahead and provide a quick hand-drawn sketch of this. Okay. And so, taking a quick look here, if we go ahead and do all the usual steps here, one of the first things that we might do is go ahead and factor the numerator and denominator and see if there are any common factors that cancel out. Okay, so if I factor the numerator, we could factor out a GCF and call that x times x minus 1. And then the denominator, that's just a linear, so that is not going to factor for us. And we can see here that after factoring everything, nothing is going to cancel for us. There's no copies in the same in the top and bottom. So as far as wholes are concerned, that would be none. Remember, if there were any common factors that canceled out, we would have a hole at that x-coordinate, and then we'd have to go through and find the y-coordinate, etc., etc. To find the vertical asymptotes, we just need to go ahead and set our denominator equal to 0 and then simply solve. Our denominator is really simple here. It's just x plus 1. So x plus 1 equals 0. If we solve that, subtract 1 from both sides, we're going to get x is equal to negative 1. And so that is going to correspond to our vertical asymptote, which I might just go through and take my, my straight edge here and just go ahead and plot. Okay, so make sure to dash that in because remember that the asymptote is not a part of the final product that we're producing. It's just one of the guidelines that we need to abide by. Okay, and then we're going to go through and find the oblique asymptote, okay? And again, the way we set that up here in the steps is that number 2, we're going to divide using long division here. So let's go ahead and set that up for ourselves. I'll come down here where I got some room. My divisor here is x plus 1, and my dividend is x squared minus x. We're just going to go ahead and use some long division to divide these two, and then continue. So don't forget how long division works. We are always going to compare the first term of our divisor, our dividend by the first term of the divisor, and then divide the two. Okay, so it looks like x squared divided by x would just simply be x, and then if I distribute x to both terms there, that's going to give us x squared minus, or not minus, it's going to give us plus x. And so here, if we go ahead and subtract the two, okay, again, paying very close attention to the signs here. It looks like your x squared is going to cancel for you, but here you've got, in this order, a negative 1x minus a positive 1x. And so that's not going to make 0, that's negative 1 minus 1. That's going to make negative 2x, actually. Okay, and so continuing here, if I go ahead and just simply multiply times a negative 2 and distribute that in, that's going to give us negative 2x minus 2. And it looks like we don't have anything right here to go ahead and subtract, but that is just going to have to be something that we interpret as a plus 0x on our on our, or sorry, not plus 0x, but plus 0, and then we drop that down. That would just be a plus 0 there. Again, we've talked about long division before. We've seen these cases, in which case we could see here that our x terms are going to cancel, and then here again, watching the signs, it's going to be 0 minus -2, minus negative changes to plus, so that's going to give us a remainder of 2. Okay, but remember that we don't pay attention to the remainder whenever we are trying to find an oblique asymptote with long division. All we need to pay attention to is simply just what our quotient turned out to be here, and simply that is going to be x minus 2. So up here I'm going to say that. I'm going to say y is equal to x minus 2. And again, the reason why it looks like an mx plus b looking equation instead of a Hoy or a Vux is because this is an oblique asymptote. This is a diagonal. So what we should always expect for your oblique asymptote is something that does look like y equals mx plus b, because it is going to be a diagonal line in the coordinate plane. And so if I come up here to the graph and plot that, we just need to go ahead and interpret that in terms of mx plus b. So here it looks like playing the role of m is just simply 1. That means for every 1 unit that I rise, I run 1 unit. And then it looks like here playing the role of b is going to be that minus 2. And so that is going to be the y-intercept. That would correspond to a point with coordinates 0, -2. Okay, so just a little bit of algebra review there. So to plot that oblique asymptote, I'm just going to come down here to -2 and plot that point, and then use my slope to get the rest of the line here. So again, it's just going to be diagonally going up like that. And so if I take my straight edge here and line that up, we can go ahead and get that other dashed line in here really easily, okay? And so that is going to be the steps that you will take to find your oblique asymptote. You just need to use a little bit of long division and figure out what that quotient is, and then leave off the remainder plus divisor part. And then, of course, we can go ahead and get the domain after graphing the rest of this. And so here is where we would come up here to the table, and we would plot this function using our TI-84 calculator. We would get some inputs. If you don't have a TI-84, you're just going to have to pick some inputs yourself and plug them into your function and see what the corresponding outputs would be. But I already have that ready to go over here off to the side. So here's a quick picture of what this graph would look like if you were to actually plot it in the TI-84. You'll notice I've graphed the actual path of the function here in blue, and then I actually have that asymptote there in that dotted gray line. So that is what our final product is going to look like, and I've actually also gone ahead and grabbed a screenshot of the table from the calculator. So just to be clear, y1 in blue here, that is my actual function, and then what it says here, y7, that is the asymptote. So if you wanted to plot more points on that diagonal asymptote there, that oblique asymptote, you can go ahead and do that gray column. But we're focusing on the blue column here. Some points here that I think would give us a really good set of coordinates to plot would be -3, -6, maybe -2, -6, and then 0, 0, and 1, 0. Those would be good to plot. Even ones that have the 0.5s on them, like maybe say here -5, -7.5, 3, 1.5. Those would be easy to plot because the 0.5 just goes in the middle of a grid square. We just need to have enough to where we are actually going ahead and getting a nice idea of what this graph is going to look like. So if I go through and plot these points real quick, which I'll just do real fast, we're going to get the following here. So let's see, that's going to go down 7.5. So my picture is not perfect. So it looks like I'm going to be crossing about right there-ish, but works out for us, right? So let's go ahead and graph some other ones here. So -3, -6 would be approximately right there. Again, just going through and plotting all the points. Boom, boom. And then it looks like this part of the graph, according to my picture from over here, that is going to look like that right there. So I might just go ahead and come through and just graph that part just like that. The other parts here, so 0, 0, and 1, 0, plot those points. We also have 3 and then 1.5, something like this. And again, we know according to the TI-84 what this is approximately going to look like here, so we can just go ahead and connect those points there. And then remember that the end behavior of our curve is going to indefinitely approach those guideline asymptotes, but it's never going to touch or cross, okay? And now we come to the domain. So again, when you look at the domain here, I always want you to remember that magnet analogy, right? Picture that we're in class and that I put some magnets up on the board at each one of these inputs on X, and then picture yourself dragging those magnets up or down to touch the graph. It doesn't necessarily matter that you're going to be crossing over one of the asymptotes in order to get to the graph. It just matters, can you drag that magnet up or down to touch the graph? I think you're going to find that you're going to be able to do that for all of these inputs here and for all of these inputs here, okay? You're going to be able to drag that up to the graph, but that problem magnet is going to be this one right here, because that is where I've put that vertical asymptote. And so when we go ahead and point out our domain, we're going to have to account for that. So that's going to be from negative infinity all the way until we put our vertical asymptote down. So that's going to be at -1. And then we're going to unite that set with the set from -1 all the way to positive infinity. And that's going to be our domain for this function. Okay, so always stick with that magnet analogy. I feel like that really works out pretty well. Here in the next example, I've already done this one in its entirety just to be able to kind of show you how this works and save some time. Here's what it would look like in the TI-84 along with the screenshot for the table. Again, just picking some points, going through and calculating all the different things that you need to calculate, setting the denominator equal to 0 and solving. That's just x squared is equal to 0. X would be equal to 0 in that case, so just the y-axis would be your vertical asymptote. And then to get your oblique asymptote, we just need to go ahead and perform that long division, okay? I don't want you guys to forget that you really do need to make sure that when you do long division, you do need some placeholders for terms that you're missing. So in our dividend, the polynomial on top, we are missing our x term, so you notice that I put that in there as 0x. And then as we kind of go through here, you are just going to be left with a remainder of 4, but keep in mind we don't use that whenever we want to write our oblique asymptote. We just go ahead and use the quotient that we got without the remainder over the divisor here. So that's going to be -x plus 1, and so y equals -x plus 1 is our oblique asymptote. And so I've gone ahead and plotted the y-intercept and then just used the slope to get the rest of the oblique asymptote before I dash that in there with my straight edge. And then you can see here, according to the TI-84, what this graph is supposed to be looking like. And so just kind of getting an approximation for that is something that we would really be wanting to do. So that's all I have for this video. Again, just talking a little bit about oblique asymptotes, recalling a little bit of long division here. That's going to be really important. Really make sure that you stick with these steps in this order so that you can be able to do these problems correctly. And then also remember, you know, if you ever have an example that has a oblique asymptote, it's automatically never going to have a horizontal asymptote. So that's all I have for this video, guys. Thank you very much for your attention. Let me know if you guys have any questions, and I'll speak to you in the next one.